Assalamu alaikum dear students. So today we are going to learn how to evaluate triple integrals. So we have already defined integrals, single integrals for functions of one variable and double integrals for the functions of two variables. So similarly, we can define triple integrals for the functions of three variables. And let's start with the simplest case where function f is defined on a rectangular box B, which is expressed here. And this box, for this box, x lies between a and b, y lies between c and d, z lies between r and s. That is, limits for upper and lower bounds for all the variables x, y, z are constant. And this is the box generated by the limits. So we can write associated iterated integral using Fibonacci theorem for triple integral like this. So triple integral over the region B, that is the box B, of fxyz with respect to the volume element dv is equal to this, where dv can be any combination of dx, dy, dz. This is one of the combination. This is another combination, dy dzx. We can write dx, dz, dy, and so on. It can be written in 6 different forms. So let's learn the process with the help of an example. So in this example, we have to evaluate this triple integral over this box B of x, y, z square dv. So let's first of all convert this triple integral into an iterated integral like 0 to 1, since x lies between 0 to 1, negative 1 to 2 because y lies between negative 1 and 2, and 0 to 3 since z lies between 0 and 3, x, y, z square. So since the internalmost limit is for z, so we will write here z, dz, and then dy, and this is the outermost dx, and this is equal to, so first of all we have to integrate this with respect to z, keeping x and y constant. So we have 0 to 1, negative 1 to 2. So we have z square here. Integral of z square is z cube over 3. So x, y, z cube over 3, and 0 to 3. Z is equal to 0 to z is equal to 3. So dy dx. And this is equal to 0 to 1, negative 1 to 2. So let's plug in the limits. So we have 3 cube divided by 3 is 3 square. So 9xy minus, when we plug in z is equal to 0, then this becomes 0. So we are left with 9xy, and we have to integrate it y first and then with respect to x. And this is equal to 0 to 1. Let's integrate this with respect to y, keeping x constant. We have 9 divided by 2 xy square, and limits for y are negative 1 and 2, and this is equal to 0 to 1 when y is equal to 2. This is 4 divided by 2 is 2, so we have 18x, minus when y is equal to 1, this is 9 by 2x dx, and we can write it as 27 divided by 2 x dx. So let's integrate this with respect to x. 27 by 4 x square, 0 to 1. So when we substitute x is equal to 1, we have 27 divided by 4, and when x is equal to 0, this becomes 0. So this is the answer. So next we define the triple integrals over general bounded region, the way we defined double integrals over general planar regions. So in this case, we are going to define these triple integrals over general bounded regions in 3-dimensional space, that is over a solid. and the process is same. We can write this integral in this form. If E is the solid, we'll evaluate triple integral of fxyz uh, over the region E, and there are different types of region, just like there were different type 1 and type 2 regions in double integrals. Here we have different types for uh, solids in 3 dimension as well. So let's discuss type 1. In this type, this is the solid E, and this is bounded below and bounded above by the functions of xy, u1 xy and u2 xy, whereas the region D is the projection of this solid onto this xy plane. So xy belongs to this region D, and these can be determined with the help of the methods we have already learned in case of double integrals. And there is another type where the solid is bounded above and bounded below. In this case, x is bounded below and bounded above by the functions of y, z. So next target is to find y and z, and for this we will consider the projection of this region onto yz plane. And this is the planar region in the plane yz. So yz again can be determined by any of the types we have already learned in double integrals. So the third type of E, region E, in this type we can determine y as the variables of x and z. That is, y is bounded below and bounded above by two functions of xz, whereas xz belongs to the region D, and region D is the projection of this solid onto the plane xz. And again, this region can also be determined by the by any of the types of double integral we have already learned. So let's discuss this method with the help of different problems. So these are the problems from section 15.6 of your textbook. So first of all, let's solve. In question number 9, you can see all the limits are already given. So this is just a matter of integration. You will write this integral as an iterated integral, and then you'll solve it. So this is the interiormost limit when z is function of x and y. So x minus y is the lower limit for z, and upper bound for z is x plus y. And then we have y, which lies between 0 and x, and then we have x, which is bounded by two constant values, 0 and 3, and we have to evaluate y. So since this is the bounds for z, so dz first, and then dy, and finally we have dx. So you can solve it yourself. Similarly, question number 10, we already have all the bounds for all the variables. In question number 11, this is also easy. You can have these bounds and evaluate this integral over this region. So let's try question number 12. So in this question, we have to evaluate the triple integral of the function sine y over the region E, where E lies below the plane z is equal to x and above the triangular region with vertices 0, 0, 0, pi 0, 0 and 0, pi 0. You can see all the z coordinates of these 3 points is 0. That is, these points lie on xy plane. So first of all, we have to determine what is the lower bound and upper bound for z. So lower bound for z is can be observed by these values, that is z is equal to 0. And upper bound of z can be determined by this plane, because if you read it again, E lies below the plane. So that is the upper bound for z. Z is equal to x. Okay, now let's draw this region in xy plane. So for xy plane, this point becomes pi 0, that is somewhere here. And this is origin 0, 0. And this one is 0 pi, somewhere here. So join these 2 points to form a line. So this is the triangular region with the vertices 0, 0, 0, pi 0, 0, and 0 pi 0. Okay. So this triangle is the triangle bounded by these 3 lines. So equation of this line is y is equal to 0. Equation of this line is x is equal to 0. Whereas equation of this line can be determined by 2-point formula. That is y minus 0 is equal to its gradient or slope is -1 times x minus pi. So this becomes y is equal to -x plus pi. So equation of this line is y is equal to -x plus pi. Okay, so we have already determined the limits for z. So this is the region D, which is bounded by 3 lines. So for D region, let's figure out the upper and lower limit for x. So you can see that minimum value of x in this region is 0. So x is more than or equal to 0. And maximum value in this region for x is pi. So x is less or equal to pi. And y is bounded for bounds of y, we can draw the vertical lines. We have already learned this in previous video. So y is bounded below by this line. Along this line, y is equal to 0. That is, y is more than or equal to 0. And y is bounded above by this line. And along this line, y is equal to minus x plus pi. So y is less or equal to -x plus pi. So let's write it 0 to -x plus pi. And then we have limits for x, that is 0 to pi. And we have to integrate sine y. Now this is limit for z, so dz comes first, and then dy, and then dx. Okay, let's evaluate this by integrating one by one with respect to z, y, and x. So first of all, we are going to integrate this function with respect to z. So z times sine y, and the limits for y are 0 to minus x plus 0 to x, sorry 0 to x, and dy dx. Okay, this is equal to 0 to pi, 0 to -x plus pi, and when we substitute z is equal to x, we have x times sine y. And when we substitute z is equal to 0, this becomes 0. So we are left with x times sine y dy dx. Okay, now integrate with respect to y. So we have x cosine y, negative cosine y, 0 to -x plus pi, and dx. Okay, so for y is equal to -x plus y, this becomes cosine -x plus pi, and plus that, since this is negative, so negative is positive, plus x cosine 0. Okay, this is equal to 0 to pi. We have minus. Now cosine pi minus x is equal to negative cosine x. So this negative will make it positive. So x cosine x plus cosine 0 is 1, so plus x. Now this is the definite integral, single integral, and you can do it yourself. So rest of the calculations can be done yourself. So this is how you can integrate a triple integral over a general region E. So let's try another example. We will be just determining the type of region and finding the limits. Then rest of the process you can do yourself. So for this, let's try question number 13. We have to evaluate this integral 6xy dv over the region E, where E is the solid that lies under this plane. C is equal to 1 plus x plus y above the region in xy plane. So for z, lower limit is z is equal to 0, because at xy plane we know that z is equal to 0, and upper limit for z is 1 plus x plus y. And rest of the limits, that is the region D, is bounded by these curves. So first of all, we are going to write z is bounded below by 0 and bounded above by 1 plus x plus y. 6xy, and since these are limits for z, so dz comes first, and in order to find rest of the limits, we are going to draw the region on xy plane. So these are the curves on xy plane. So let's draw these. Y is equal to 0 is x-axis, that is, this is the line. Y is equal to 0, and y is equal to x, square root of x is the branch of the parabola which lies above x-axis. This is y is equal to square root of x, and x is equal to y is 1 is the line parallel to y-axis. This is x equal to 1. So this point is 1, 0. And since this point also lies on the line x is equal to 1, and when x is 1, y is also 1 on the curve. So point of intersection of curve and the line x is equal to 1 is 1, 1. So this is the region D on xy plane. So that is, we have to determine x and y from this region. Okay, in this region you can see that x minimum value of x is 0 and maximum value of x is 1, whereas y is bounded below by this line, and along this line y is equal to 0, that is y is greater or equal to 0, and bounded above by this curve, and along this curve y is equal to square root of x, so y is less or equal to square root of x. So 0 to square root of x, so we have dy here, and x lies between 0 and 1, so we have dx here. So this is how this integral can be transformed into an iterated integral, and rest of the calculations can be done by yourself. So solve this to evaluate the integral yourself. Okay, let's try one of the applications of the triple integral, and one of the it is really hard for us to visualize this triple integral of some function of three variables over a solid E. As we know that the integration of function of one variable within over the interval AB can be visualized as area under the curve above the line above the interval a b bounded by the lines a is equal to x is equal to a and x is equal to b. So this integral is equal to, it represents this area, whereas this double integral of the function f x y over the region planar region D represents volume under the surface and above the region D. But this is really difficult for us to visualize this integral. So there are few other applications of this triple integral, and the particular case when f x y z becomes 1, then this integral becomes volume of the region. So if we have to find volume of the region, then we have to integrate 1 over the region E. So let's apply this to find out volumes of different solids. First of all, we have this example. Use a triple integral to find the volume of the tetrahedron T bounded by the planes x plus 2y plus z is equal to 2, x is equal to 2y, x is equal to 0, and z is equal to 0. So since we are required to use triple integral to find the volume, so we are going to use this formula just we learned in previous slide, that we are going to integrate 1 over this region E. So in order to find all the bounds for all the variables, first of all, let's try to find the bounds for z. So z is bounded below by 0 and z is bounded above by this z is equal to 2 minus x minus 2y. So you can see this is the solid actually under this plane and above this region. So in order to find this region, we have to find out the projection of this solid onto xy plane. So projection of solid onto xy plane actually consists of the region bounded by 3 lines, x is equal to 2y, x is equal to 0, and x plus 2y is equal to 2 when z is equal to 0 along this plane. So this becomes x plus 2y is equal to 2, which is a line. So this is the region D. So in order to find limits for x and y, we'll use this. So this volume integral becomes, let me write all the limits. Z is bounded below by 0, z is bounded above by 2 minus x minus 2y, and this is the region, and you can see minimum value of x is 0, maximum value of x is 1 in this region. So limits for x are 0 to 1, and then y is bounded below by this line, and along this line y is equal to x by 2, and y is bounded above by this line, and along this line y is equal to 1 minus x over 2. So x over 2 to 1 minus x over 2 dv. So after integrating, we have this answer, which is equal to 1 over 3. Okay, let's try a few questions from exercise. Again, the same exercise 15.6. Let's try question number. This is same as the question we just solved in previous slides. And let's try question number 21. So we have to find the volume of the solid using triple integral, and the solid enclosed by the cylinder y is equal to x square, and the plane z is equal to 0, and y plus z is equal to 1. So for this, first of all, write the formula for volume, that is we have to integrate 1 over this region E, where E is the region enclosed, solid enclosed by the cylinder y is equal to x square, and the plane z is equal to 0, y plus z is equal to 1. So first of all, find limits for z, and you can see from these two equations, z is bounded below by 0 and z is bounded above by 1 minus y. So 0 to 1 minus y, and then we have to find the limits for x, y. For this, let's draw the region D on xy plane. That is the projection of this solid on xy plane, and that would be when z is equal to 0, y is equal to 1. So this line, this is the line, y is equal to 1, and y is equal to x square. The projection of this cylinder is the curve y is equal to x square on xy plane. So this is the curve y is equal to x square. So in order to find the points of intersection, if we have y is equal to 1, so x square is equal to 1 means x square is negative 1 and positive 1. So y is 1 for both the points. So negative 1, 1 and 1, 1. So these are the 2 points of intersection. And this is the region D. Xy belongs to D. And Z we already have determined the lower and upper bound of Z. So you can see that x is less or equal to 1, more than equal to negative 1, that is x lies between minus 1 and 1 in this region. Whereas if we draw vertical lines, so y is bounded below by this curve, and along this curve y is x square, so y is greater or equal to x square, and y is bounded above by this line, and along this line y is equal to 1, so y is less or equal to 1. So let's write the limits here. X square to 1, these are the limits for y, and bounds for x are negative 1 and 1, and dv then becomes dz dy dx. So okay, let me complete this. Let's do the integration part as well. For this, negative 1 to 1, x square to 1, so we have to integrate with respect to z first. So integral of 1 is z, and limits are 0 to 1 minus y dy dx, and this is equal to negative 1 to 1 x square to 1. When z is 1 minus y, this becomes 1 minus y. When z is 0, this becomes 0, so we are left with 1 minus y only, dy dx, and this is equal to negative 1 to 1. And when we integrate this with respect to y, we have integral of 1 is y minus y square divided by 2. Okay, x to 1 other limit, so dx. All right, this is equal to negative 1 to 1. So let's plug in the limits. We have, when y is 1, 1 minus 1 over 2, this gives us half, and when y is x, this becomes minus x and plus sorry, there it was x square here, I forgot, minus x square plus x 4 divided by 2, and we have to integrate with respect to x. Okay, this is equal to half of x minus x square cube, x cube by 3 plus x 5 by 10, and limits are negative 1 to 1. Now you can verify it yourself after plugging in the limits and some manipulations. We'll have 8 over 15. So that's all for today. Bye.